Fusion is where it all comes together to make planning simple.
Welcome to Talking Autonomy. In previous episodes, you've heard about ghost vision, you've heard about ghost radar, you've heard about lane perception, and this is where it all comes together, fusion. My friend Prannay here is going to walk us through the process for how we take all those different signals and turn it into an actual view of the scene that we can drive through. So Prannay, welcome to Talking Autonomy.
Great to be here, man.
Prannay, why don't you introduce yourself real quick? What do you do for Ghost, and what have you done in your career before here?
So I'm a model engineer. I work across the stack, and I'm responsible for putting it all together and writing out the drive program and so on. I have a computer science degree, and before this, I spent my time in high-frequency trading, where I was mostly, again, looking at noisy data, trying to extract signals. So a lot of similarities there, and focusing on the high SNR problems.
Yeah, it's really interesting to hear about how the work in high-frequency trading kind of translates to driving, and although they're very different domains, there's a lot of commonality between them.
I think it's in the end just simple regressions everywhere, and building pipelines and building workflows which allow you to work with a lot of data consistently for a lot of use cases, and finding ways to scale it out, finding how it all generalizes, testing that rigorously. So all of those things just immediately translate, and the rest of it is just applying different first principles.
All right. Well, let's get into some of the details here, at least on the fusion dimension of it. So why don't we just start at a very high level? Can you explain to us what fusion is all about? And I think you brought some visuals that can kind of show us what happens under the hood.
Yeah, I mean, fusion is basically the point where you have all your inputs coming in. You have multiple sensors. From the same sensor, you're extracting signals in different ways. You're trying to understand traffic flow. You're trying to understand obstacles. You have vision. You have radar. You have lanes. You're trying to put it all together to construct the scene that you can plan off of. And this is where a lot of things get interesting, because you don't just care about the calibration of one sensor. You care about the calibration of all the sensors and how they relate to each other. So on the scene here, you can basically see on the red, we have the information that's coming from radar. In the green, we have the information coming from vision. And then we overlay them together and find the best likelihood position of obstacles. We also understand how it is all flowing over time. And we put it in the context of lanes, and that actually tells us, okay, what is the velocity of our current lane? What's the velocity of the lanes around us, right? Because we have to control for everything in order to give maximal amount of safety and comfort. And extracting all of that information into very simple to understand scene variables is basically the name of the game here.
Well, and I guess one of the opportunity comes from the fact that we essentially have multiple sensors that are looking at the same scene just in their own way. So you have vision that is detecting obstacles, but also giving you distance, giving you velocity. You have radar that's detecting obstacles as well and giving you distance, giving you velocity.
Yep.
And so the fusion is kind of bringing these two different modalities together into one view.
Yeah, that's right. And the interesting thing about fusion is that it helps you correct for errors in interesting ways, because the radar unit sits in a different place in the car. It is exposed to different kinds of noise with the car pitching up and pitching down. The cameras, they're in a more stable position, but cameras are limited by how far they can see. Radar is limited by a lot of false alarms close by, and we have seen a lot of other companies get into trouble with things like that. So our approach has been to basically try to use them where both of them shine. So vision will nearly never miss anything close by. Radar will nearly never be bad at estimating velocities. So fusion is where we go and correct for errors between different locations, but also in the different modalities in the data, because they just, in the end, it's all electromagnetic waves, but how you measure them really matters. And you're kind of working in different frequency domains, and that is why you're able to extract the signals in different ways at different frequencies and stuff like that.
Okay, so we'll get into a little more on kind of where each of them shines and how to think through that process in a second. But when people talk about fusion, there's often a debate between whether you do early fusion or late fusion. I'll spoil the surprise, we do late fusion.
Yeah.
But why don't you describe the two approaches and why we do late fusion?
So the reason picking where you do fusion is interesting is because that determines what your debugging development cycle looks like for each of those signals and the outcomes you derive from it. So early fusion versus late fusion determines when you build your models, at what the point at which you combine your information has to be the point where you have maximal amount of signal to noise ratio to do that. And for early fusion, that usually means that you're trying to combine them as early as possible because you want access to the most raw amount of information, most maximal amount of information, and then you think that you'll be able to generate signal from it anyway. Late fusion approaches are usually around saying that when I have too much information, it is harder for me to extract the signal from it. So you want to compress the information down to just a very just the signal part of it essentially, and then you have these two sets of signals coming in or three sets of signals coming in, and you want to combine them at that point. And our approach has been to stick to late fusion for multiple reasons. The biggest one being that the development productivity we get with that, and our ability to switch between different sensors in different, for example, different vehicles, or if we want to do partial hardware upgrades and mix and match, or to handle sensor failures, has been really simple, and it's been very easy to think about for us to think about it. While in early fusion, some of these problems are a little more hairy, even though we are giving up on extra information in some sense, which sometimes is noise, but sometimes is also signal.
Well, my understanding is also that part of the reason why a lot of the early approaches used early fusion was because you had radar that was maybe not quite as intelligent as current auto radar, and so there was a lot of noise, and it was pretty important to fuse it with a camera early on to get a sense for, okay, the camera found a car here, so I can listen to the radar in that specific spot and ignore all the noise in the rest of the scene. It's kind of the only way to filter through the noise in the radar. Yep. But we're in a position where we have a very mature vision stack and a very mature radar stack, and we're trying to kind of treat each independently. And so late fusion kind of allows us to reason about each of them independently.
That's right. And with the software-defined radar, that gives us the ability to feed back information without having to do early fusion. And it does not preclude us from our ability to handle all of the noise downstream, because a software-defined radar usually also gives us a much denser signal for the point clouds that we're looking at.
Okay, so give me some practical examples. I mean, because we're doing late fusion, we can, in different situations, maybe rely more, listen more to vision signals versus radar signals and other pieces of information. So give me some situations about how we think about those differently.
Yeah, I mean, let's say you're driving on an open road, right, highway, and you're seeing obstacles very far away from you. Now, in vision, these are going to show up as like really small obstacles, right? And like that's true for humans as well, that we usually just see something very far. We don't have very accurate perception of its velocity. We just kind of have this idea of, okay, it's expanding towards us or not, and then we just keep driving that way. And this is where radar will shine, because you're going to have very accurate velocity, and what that allows you to do is do both comfort and safety. For comfort, it's like you want to appropriately start slowing down into traffic if you see density ahead of you, right? And figuring out density is much easier from radar than it will be with vision, and so is velocity. But now when you're in a, let's completely switch the situation, where now you're in stop and go traffic. And in stop and go traffic, the most important thing is to make sure that you see everything around you, right? And you want to have a very low latency system. You do not want to have any lag in the system. And this is where vision will shine, because you will see everything, even if it's very up close. And when you're in really dense traffic, radar often has all of these multipath problems and side lobes. You have trucks which have detections coming from different parts of the truck, from the wheel, from under the truck, from behind the truck, and all of that. And vision really is much simpler, and you only see what is around you, right? And in this case, vision will completely shine, right? But this kind of is telling you that are you just like switching modalities when you go from one to the other? And this is where life gets interesting, that if in every domain you have one modality which is in some sense superior, right? But has its quirks that, for example, even in stop and go, you want extremely accurate velocity. So once you know where everything is and what you care about, figuring out its velocity from radar is really simple, right? And on the other hand, if you go back to our open road scenario, right, and you're driving on open road, you see something really far away, right? When something is really far away, you do not know its height. So there is no way you can differentiate between a fire truck and a bridge. And that is where vision comes in, and that it allows you to do that. So
Yeah, it's not about one or the other. It's just
That's
about
right.
using the different signals you can get out of each modality at different ways. And I mean, we're just talking near and far, but there's differences in weather situations where vision might be affected by weather, and radar can pierce through some of that. There's differences in tunnels.
Yep.
All types of things.
So yeah, actually, when the weather one is really interesting because yes, there are occlusions, and vision as a modality is really sensitive to even small occlusions like salt, and we handle all of that, but having radar obviously helps because at that point you know what your ground truth is, and it's really easy to disambiguate between is this just there's actually something there or is this just noise. And again, that's where fusion comes in. And I think that tunnels are particularly interesting for fusion because when you go inside tunnels, suddenly the scene becomes really dark, right? And there are often a lot of reflections in the tunnel from radar, and that is where suddenly both of your signals start showing their error modes. But when you fuse them together, they will only agree where there is actual information, and everything else will one modality or the other is just going to reject it, right? And I think that so hence. And doing tunnels is interesting for a various set of purposes because GPS doesn't work there, and as I said before, we combine everything that we have from information from lanes as well. And sometimes the only way to drive in tunnels is through obstacle information and controlling against the obstacles in the scene, and that is something that can only happen if you combine your entire scene at some place and put all the relevant information to extract the right scene variables out.
Fascinating. Lots of different cases and a lot that goes into fusion, just not as simple as listen to this here, listen to that there.
That's right.
I know one final topic that you spend a lot of time thinking about is calibration. And I know we think about calibrating individual sensors, but there's a calibration that happens as all the sensors come together. Talk a little bit about that.
Most of calibration is for a single sensor is focused around figuring out how is it oriented with respect to some point in the car, right? And as you move, there are going to be distortions. There's going to be road noise. There's going to be just somebody touching something, and that affects every sensor. And so a lot of individual sensor calibration is about that. Fusion is the point where when you have to put things together, and if you want to reject information, you need to make sure that you're not compounding the noise from errors in your calibration. Nothing's going to be perfectly calibrated. And it actually also kind of opens up the question that can you even do fusion if you do not have proper sensor-to-sensor calibration? So our solution has been that solving the problem of fusion and solving the problem of correcting for errors, small errors in calibration happens at the same time, where you simultaneously have to go correct for the errors, find the most likely fusion, and then go back and ask the question, okay, with this fusion, how consistent is the errors that I thought I have in the system than I calculated? And this is a feedback loop that you run with all your sensors and across time to converge to whatever error you have right now and to improve your fusion estimates. So that, and I think that really also goes back to the question you were asking earlier of late fusion versus early fusion. Extracting maximal amount of signal, the purpose of that was to be able to combine information in order to do two things, which was both calibration and fusion and not just one or the other, assuming that the other thing worked. Right? For example, you don't want to assume your calibrations work.
So it's inherent to the process, it seems like.
That's right.
All right, so there you have it, fusion, where Ghost brings together visual perception, radar perception, lane detection, all into understanding and fusing together a single view of the scene so that we can drive. Prannay, thank you very much.
Thanks, man.